So get your quizzes out. Quick reminder, when's your test? Friday. When am I doing a tutorial? It'll be tomorrow after school. Okay? So as to make the French immersion students happy. Sorry? Oh, thought you were talking to me, Mitch. Indoor voice. Mark your own. Here we go. Number 1. So, orbital speed. I'm almost certainly going to be asking you to do this on your test on Friday. We're in orbit. When I'm in orbit, my first inclination is to think, well, gravity is pulling me in a circle. Big G, big M, little m over r squared, or m1, m2 over r squared equals. Don't forget the little m, because force is mass times acceleration, and the equations in your formula sheet are acceleration equations, not force equations. Which acceleration? Oh, they said speed. I'll use the v squared over r. Yay, a mass cancels. And let's get the v by itself. I think this was the one we ended up with, v equaling big square root of, oh, and an r cancels, Mr. Dueck, by the way. Yeah, v equaled the square root of big G, big M over r. It's going to be the square root of 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, divided by, did they give me an altitude or a radius? Oh, they gave me a radius, so I don't need to add the radius of the Earth. I would if it was an altitude, but this is just a radius. 9.6 times 10 to the 8th squared. Nope, one of the r's canceled. Let's see. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th divided by 9.6 times 10 to the 8th. Square root of that. Do you get 644.6, or am I wrong? Yep, people nodding? 640, I guess 5 if I go to 3 sig figs meters per second, or 640 meters per second. In terms of part marks, if you got it, you get it 2 out of 2. Otherwise, I'd probably go half mark for that, half mark for that, half mark for that, and a half mark for the answer. B, what's the kinetic energy? Well, kinetic energy hasn't changed since physics 11. It's a half mv squared. It's a half little m. What's moving? The 3500. 645 squared, but I'm going to use the exact value I have on my calculator here. Squared times 3500 times a half. And I get 7.27 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Joules. Half mark. Half mark. 1 mark. Now if you got the wrong answer here, but Mitch, you went a half m wrong answer squared and did it right, give yourself 2 out of 2 for whatever you got here. Example 2, same as question 2, same as question 1, except here they want the period. I'm going to start out the same way. Brianna, I'm going to go, well, gravity's pulling me in a circle. Gravity is big G, big M, little m over r squared. Circular force is m. Oh, I'll use the 4 pi squared r over t squared. Okay, the mass cancels. Sadly, that's all that cancels. They want the orbital radius. R ends up being the cube root of g m t squared all over 4 pi squared, I believe. The t squared would move up there, the r cubed would move, yeah. equals the cube root of 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 36,000, which is 3.6 times 10 to the 4th. Divided by 4 pi squared. Okay, 6.67. One button. Times 10 to the negative 11. Times 5.98. Times 10 to the 24th. Times 30. Whoop. No times hit, Mr. Come on. Times 36,000 divided by bracket 4 pi squared, close bracket. Cube root of this, math, cube root. You get 713821999, 7.14 times 10 to the 1, 2, 3, 4, 5. Is that right? Why is it technically wrong? Why have Mr. Dueck made up bad numbers? What's my orbital radius? Katie, what's the answer I got here? What's the radius of the actual Earth itself? Times 10 to the what? 6? And here I got an answer of 10. I've made up an impossible question subterraneously somehow inside the Earth. Oops. Sorry. The numbers work, but the physics actually doesn't. My questions on the test are better. Anybody notice that and go kind of, hey, what the heck? No one did? You guys were all okay with like Star Trek phasing through the planet or something? Okay. What's the gravitational potential energy of the satellite relative to 0 at infinity? Okay. Come on, pen. Potential energy is equal to negative big G, big M, little m, all over R. And the reason I know to use this and not use MGH is I'm in space, and that phrase, relative to 0 at infinity, that's our trigger phrase, that's our code. Hey, Brett, use the cosmic potential energy, please. Negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24. 1600. Divided by 7.14 times 10 to the 5th. 6.67 times 10 to the negative 11. Yeah. Aren't I supposed to square 36? Ah! Squared, Mr. Dueck. So maybe I did the other one wrong? Is that what you're saying? So I was going, I don't recall finding it inside the planet before. So when you all said you got the same answer, some of you must have been lying or did the same mistake as me. Well, and somebody tell me when I say, okay, that, and then cube root this. You get this, 2.357, you get this? Okay, times 10 to the 1, 2, 3, 4, 5, 6, 7. Oh, thank you, I did make up good numbers. 2.36, I guess. Times 10 to the 7. Is that the right answer? Yes or no? Brett, what did you get? That? Okay. Did someone else get this? You got that? You got that? Yeah? No? Yeah? Okay. If you didn't, probably made a calculator mistake or did the same dumb thing I did, forgot the squared. Yay, this is legal. I'm not orbiting inside the planet somehow like a freakish Star Trek phasing starship or something like that. So let's try this again. Thank you, Nicole. Candy for you. Negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 1600 divided by my last answer, which was 2.36 times 10 to the 7th. Do you get negative 2.7076, 2.71 times 10 to the 10th? Yes? No? Yes? No? I think that's right. Pretty sure that's right. Here, 1 mark, 1 mark, 1 mark. Turn the page. Oh, by the way, if you're getting all the right numbers and the wrong stuff on your calculator, I think your physics teacher mentioned that it was important to practice with your calculator. Brett, you have something to share with us? Shouldn't make a difference. You haven't hit sine, cosine, or tangent. Oh, it doesn't matter. Otherwise, I probably would have suggested that as your first mistake. But since you haven't hit the sine or cosine or tangent, sorry, squared is squared in radians or degrees. Nice try. Number 3. How much work does this require? Are we in orbit? Well, when they say lifted, that implies no. We're going to start out by saying, well, work is the change in potential and the change in kinetic. Except, Joel, since we're not in orbit, I think we're starting at rest and finishing at rest. Lifted seems to imply that. Joel, what's changing anything? There's final minus initial. Let's plug in numbers. Negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. What's the second mass? 5,000. All over. Now it does say to an altitude, so my final radius is going to be the altitude plus the radius of the Earth minus negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 5,000. And we're starting off on the surface of the Earth, so my initial radius is 6.38 times 10 to the 6th. All right, I'm going to type in the first expression, press equals. So negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 5,000 divided by bracket 5.4 scientific notation button. Whoop. Scientific notation button 5 plus 6.38 scientific notation button 6. My final potential energy is negative 2.882. Negative 2.882 times 10 to the 11th. And then I have a minus minus, which is a plus. And I'm going to get clever. I'm just going to delete the minus sign. And if I delete the altitude, I think that's the numbers that I had there. Enter. 3.126 times 10 to the 11th. So take this number and add negative, oh, hang on, Mr. Dueck. Go negative 2.882 times 10 to the 11th. And then add my most recent answer, because the minus minus is a plus. So you get positive 2.44 times 10 to the 10th? And it's work, joules. I like number 4. Well, first of all, I like number 3. I like number 3. I like number 3. I like number 4. I like number 4. I like number 4. Except number 4 on the test is going to be slightly tougher. Here, I gave you the orbital speed. I went and calculated it. Jacob, did we calculate orbital speed in 1A? Say yes. I would have no problem expecting you to calculate the orbital speed yourself in question 4. And I think that's on one version of the test. I say, how much work? I just give you how the radius. So work is change in potential, change in kinetic. Katie, what do you want to find first? Change in potential or change in kinetic? That's what I'm asking you. Pick. Okay. What's change in anything, Katie? So this is going to be a half mv final squared minus, and I think my initial is starting from rest, 0. Which is a half m. Oh, I need to find v final. Ah, Katie, we go like this, right? In fact, you know what? Since I have it in 1A, I'm going to say I know that v equals the square root of big G, big M over R. So v squared is going to be big G, big M over R with no more square root. The change in kinetic energy is going to be a half times 2600 times 6.67 times 10 to the negative 11. I have no idea what the mass of the moon is. Can somebody look that up or read it to me? Sorry, louder. Divided by, and I have no idea what the radius of the moon is. Mitchell, what's the radius of the moon? 1.74 times 10 to the 6. Now, I got to be careful. That's not my orbital radius, because then it also added an altitude above. So I'm going to add 2 times 10 to the 6th. Here is, in theory, my kinetic energy, a half m come on, computer. V bracket you get a kinetic energy of 17040600160. Let me double check. 0.5 m big G mass of the moon divided by the radius, which is from the center of the moon out. They gave me an altitude, so start with the altitude, add the radius of the moon. Get 1.704 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. That's how much kinetic energy it needs to stay in orbit. Katie, we found that. Now what? What's changing anything, Katie? going to be negative big G big M little m over R final minus negative big G big M little m over R initial. In the interest of time, I'm going to wimp out a little bit here. This is quiz number 2, version 2. Let's go find it, Mr. Dueck. Quiz 2, version 2. Oh, I don't have a quiz 2, version 2 answers. I guess this is it. Going to be it. Never mind. I stand corrected. I got to crunch these. Thought I could take a shortcut. My bad. Okay. Negative 6.67 times 10 to the negative 11. Mass of the moon, 7.35 times 10 to the 22. Mass of the object, 2600. All over R final, which is 1.74 times 10 to the 6th plus 2 times 10 to the 6th. Minus minus, which is a plus. 6.67 times 10 to the negative 11. 7.35 times 10 to the 22. 2600. 2600? Yeah. All divided by my initial, which is the radius of the moon, which is 1.74 times 10 to the 6th. What's the change in potential energy? Let's see. Times 2600 divided by bracket 1.74 scientific notation button 6 plus the altitude. Oh boy. Oh, the open, I said bracket, I hit bracket, it didn't go. Bracket. Try that again. Final is negative 3408 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. So negative 3.408 times 10 to the 9th plus initial is going to be this same number except delete the negative and delete the altitude. 7.3255 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 7.3255 times 10 to the 9th. So the change in potential is going to end up being that number plus negative 3408 times 10. Come on, decimal. Times 10 to the 9th. Sheesh. 39175. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3.9175 times 10 to the 9th. Oh, Mr. Dueck, we're not done yet. Work is going to be the change in potential and the change in kinetic, which is going to be the change in potential 3.9175 times 10 to the 9th, plus the change in kinetic 1.704 times 10 to the 9th. Plus 1.704 times 10 to the 9th. Do you have 5.6 times 10 to the 1, 2, oh heck, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you get 5.6 times 10 to the 9th? Is anybody nodding? No one's nodding. Zay, yes, no? Sean, yes? Caitlin, no, yes, no? Did it wrong? Sorry, say that again? That's the scientific notation button on the calculator. I think this is right. 5.62 times 10 to the 9th. The way I would mark this, I'd give out lots of part marks on a test, but on the quiz, with this being stupidly only worth 3 marks, 1 mark if you found the change in kinetic, 1 mark if you found the change in potential, and then 1 mark for adding them together. Yo, dope. Come back. Yeah. It didn't give you the speed. Or, so, yeah, no, I did use it. Oh, no, I didn't. I calculated it, didn't I, for some dumb reason? Because I was demonstrating how to do that. I don't know. Apparently, I forgot that I'd given you the orbital speed here. So will that change things, Mr. Dueck? Oh, God, I hope not. But it probably will. Let's see. Can you, from now on, when I make a mistake, not wait till I'm completely done everything and then point out a mistake 10 minutes ago, but maybe right when you notice it, just point it out right then, because you're good at catching them. But, okay. A half m v squared. Please tell me that that also works out to this number here. It's close. I rounded off. So what would that do to your final answer? It would be, let me just confirm because, you know, I botched this thoroughly here. Plus 3.9175. You said 5.637, so 5.64? Yeah, 5.6 times 10 to the 9th, so you still get the same thing. Oops. Sorry. Oops. That's how you'll do it on the test, though, when I don't give you the speed. Okay? Give yourself a score on a 15. But I don't want to collect them. I want you to have them to study from. So, person on the end of each row, take out a piece of paper, put your name on it, write your name, write your quiz score, and then pass it down. So get out your notes from last day, electrostatics. We introduced you to Coulomb's law. We noticed, first of all, Mitsu, it looked an awful lot like the equation for gravity. Different letters, but it was very similar to it. I'd also like you to, if you can, take a look at your or someone else's formula sheet. So I want to talk a little bit about this unit. Almost any time we start a new unit, kids are, is it hard or is it easy? Tough? This unit mathematically isn't that challenging. Where kids really run into the wall is because all of the main equations look almost exactly alike, and they get which equation to use when mixed up. This right here is force. It's kq1 q2 over r squared. This right here is electric field, which is kq over r squared. This right here is potential energy, which is kq1 q2 over r. This right here is voltage, which is kq over r. You may have even noticed they sound a lot alike when I read them out. Nicole, I found the kids who try and cram this at the very end, who don't keep up with the homework, they'll die a miserable death in this unit. The best advice I can give you, Andrew, is don't cram. Keep up with the homework, and the formulas will fall into place. The equations will fall into place. The concepts will fall into place. But I'm telling you, if you try and learn this in the last 2 days and keep this straight from that, straight from that, straight from that, unfortunately, you're going to get zeros, because as soon as you write down the wrong equation, I can't give you any part marks because you're finding the completely wrong concept. So I give you 0. Okay? So don't do that. We left off right here. So mention formula sheet. I did that, Mr. Dueck. We talked about how there was an electrical force between charged particles. I'd given a couple of students some plastic pieces of sticks, plastic wands, and we'd charged them up by rubbing some extra electrons on them, and then we had noticed that they attracted some paper. We said that like charges blank and unlike charges blank. Like charges what and unlike charges what? You remember? Like charges repel, unlike charges attract. That's how we're going to figure out the direction. How are we going to figure out the magnitude of the force? Coulomb's law. Now, Coulomb's law, it's worth us rewriting on this page since it's a new day. The electric force we said was equal to K Q1 Q2 over R squared. Where K was just like big G, it was the electric constant, Matt. It was 9 times 10 to the 9th. Q1 was the magnitude of the first charge in coulombs. That's how we measured charge. Q2 was the magnitude of the second charge in coulombs. And R was the distance between the charges. We also said that the elementary charge, the charge on one electron, is pretty small. It's 1.6 times 10 to the negative 19 coulombs. 1 coulomb is actually a huge amount of charge. In fact, 5 coulombs would probably kill you. Certainly would damage, it would burn you. Okay? So for this unit, frequently we're going to use this right here. Look up. You'll end up memorizing this, but we're going to write it down. Microcoulombs. Microcoulombs. Mu C. And the easy way to do this is whenever you see a micro, just replace it with a 10 to the negative 6 times. All right? So now that we've jogged your memory, let's find example 4a. 4a says, find the net electric force, magnitude, and direction on the positive 1 microcoulomb charge below. So this charge here is being held in place by invisible angels, and we want to find out which way it's being tugged and how hard it's being tugged. How many charges are there in this horrible diagram here, Katie? Psst. 3. How many charges are there in this equation? 2. Here's where we use what we call the principle of superposition. That's a fancy word for saying, don't write this down, but temporarily I'm going to pretend that isn't there. Don't scribble over yours. I'm going to find, you know what? Let's call this charge A, charge B, and charge C. I'm going to find the force between charge A and B. I'll call that FAB. And that's going to be K QA QB over R squared. What was K again? This was one of the few easy constants out there to remember. Caitlin, what was K again? 9 times 10 to the 9th. Charge 1 is 1 microcoulomb. Mr. Dueck, isn't it negative? No, we said we don't put negatives and positives in for forces. We're going to decide the direction by using like charges what, unlike charges what. Like charges what? Repel, unlike charges attract. Charge B is positive 1 microcoulomb. And the distance between them is 20 centimeters. Mitsu, they're not going to get me. 0.2 squared. Go ahead. This is K. K is 9 times 10 to the 9. It's on your formula sheet. It's the constant K in this equation here. Okay? Here's the equation. Okay? Yes? What's K? That's from your formula sheet. What is it? Charge 1. 1 microcoulomb. 1 times 10 to the negative 6. Charge 2. 1 microcoulomb. 1 times 10 to the negative 6. Divided by, how far apart are they? 0.2 squared. Yeah? Yeah? Or no, yeah? And you get 0.225 newtons. That's the magnitude. Which direction? Well, again, imagine invisible angels are holding all three of these charges in place. Which way would this charge here want to move if he could, based on what this charge is? This charge, negative or positive, Nicole? This charge, negative or positive, Nicole? What about this one? Look at the number, people. Okay, you with me now? You guys are really overcomplicating this. You with me now? We're good? Are these charges like or unlike? Repel or attract? So this gets pulled to the left. Is that okay, Brett? Is that okay, Nicole? You with me? Now, hello? Now, I repeat the procedure because not only is A exerting a force on charge B, and they said they wanted me to find the force on the positive 1 microcoulomb charge. That, by the way, that's how I clued in. It was the middle charge. They wanted me to find the force on the positive 1 microcoulomb charge. This is the only one that is positive 1 microcoulombs. Now, I'm also going to find what force C is exerting on B. I'm going to find the force between B and C. That's going to be K QB QC over R squared. It's going to be 9 times 10 to the 9th. Emily, how big is the charge on charge B? 1 microcoulomb. 1 times 10 to the negative 6th. How big is the charge on charge C? Oh, over here it says negative 2 microcoulombs. I'm not going to put the negative in. I'm just going to put a 2 microcoulombs. The negatives and positives will tell us which direction. How far apart are charge B and charge C, Emily? Look at the diagram in front of you. 10 what? Centimeters. So what am I going to write? 0.1 what? Squared. Okay. I can use almost the same numbers, but I'm going to change that to a 2. I'm going to change that to a 1. And I get 1.8 newtons. What direction? Ready, Nicole? This middle charge, positive or negative? This right-hand charge, charge C, negative or positive? Unlike or like? Unlike, repel or attract? So this is going to tug this guy in which direction, left or right? Mitsu, is that okay so far? That means that my net or overall force is going to be, am I going to add these together or am I going to go bigger minus loser? Bigger minus smaller. What direction here, Emily? What direction here? So I'm going to add them together or am I going to subtract them? Yeah, right. I'm going to go bigger minus smaller to get the net force. If they were in the same direction, what would I do? Add them. So I'm going to go 1.8 to the right, take away 0.225 to the left. I'm going winner minus loser, right? To find the net force. But now we're not going MA, we're going in electric force, KQ1, Q2 over R squared. 1.8 minus 0.225, and I get 1.58 newtons. Direction. Right. You guys are a little dozy this morning. No yawning. Okay. Next page. Example 4C. What happened to 4B, Mr. Dueck? I don't know. 4C. Okay. I have a positive 1 microcoulomb charge. It's represented by this little floating dot right there. Where could I place it so that it would have no net electrical force? A, B, C, D, or E? Where would all of the forces cancel? Let's see if we can figure this out by reason. Yeah. Go ahead. Go ahead. Sorry, I can't hear you. What about negative 1 microcoulomb? What? I didn't hear a word you said. And then I heard you say microcoulomb and yeah. I don't know. Let's find out. Suppose we put it right here. Don't write this down. Just watch. Suppose we put a positive charge right there. Which way would it feel a force from this charge? What direction? Positive or negative? Positive or negative? Okay, can I stop saying that and can I just go like or unlike? Okay, can I stop saying that and simply say attract or repel? Direction. To the right. What about this guy here? Attract or repel this guy over here? Attract. Which direction? Can two rights ever cancel out to give you 0? Right? Okay. What about B? Suppose I go there. Attract or repel? Direction. Left. Attract or repel? Attract. Direction. I got a left and a right. Possibly. Which charge is bigger, this one or this one? Right-hand charge or left-hand charge? Which one's bigger, Emily? So which one will exert a bigger force? The right-hand one? So I probably don't need to be as close, because the closer you get, the stronger the force. So maybe B. What about here? Well, here, this would pull it this way. This would pull it that way. Can that possibly add to 0? No, if I add them tip to tail, I get kind of something like that, but I don't get a 0. So C, definitely wrong. I'm twigging on perhaps B. I think Brett might have been right. Let's check out E. Let's put the charge right there temporarily. Attract or repel? Attract. Direction. Left. Attract or repel? Attract. Direction. Can two lefts ever cancel out? Okay, that's definitely wrong. So it's B or D. And D also would have a force to the left, a force to the right. But this one here is a bigger charge. Being stronger, it would actually pull it in. I think the equilibrium point is location B. It says explain your answer using appropriate concepts. I think we just did it verbally. I'm not going to write all that out, but that's how I'd handle it. Find the electrical force and direction on the electron shown below. So here's an electron. The distance here is 2 micrometers, so 2 times 10 to the negative 6 meters, very small. We're talking nanoscale now, just about. also 2 micrometers. And then we have a positive 1 microcoulomb charge here and a negative 2 microcoulomb charge here. Again, you know what? How about we call them A, B, and C? Which charge are we trying to find the force on? Brianna. So I'm going to find the force between A and B, magnitude and direction. I'm going to find the force between A and C, magnitude and direction. There is a force between B and C as well, but I don't care because it wants the force on the electron, so who cares? And that's going to be K QA QB over R squared. 9 times 10 to the 9th. Oh, electron. What was the charge on an electron? They don't need to ever tell me. I know it. Mitch, you're right. Nice and loud. The elementary charge, 1.6 times 10 to the negative 19. The charge on B is 2 microcoulombs divided by the distance is 2 micrometers squared. What is the force between A and B? I get 7.2 times 10 to the negative 4 newtons. Anybody else? Nicole? Yes? Huh? Am I right or not? Yeah? 7.2 times 10 to the negative 4. Direction. Right here, what direction is the force from charge B? Which one? Positive or negative? You tell me an electron's positive? Okay, you need to know that. Positive or negative? Like or unlike? Repel or attract? Is that okay? Brianna, you're looking puzzled. Is it working okay on your calculator? Yeah? Okay. Let's also find the force between A and C. That's going to be 9 times 10 to the 9th. Charge A, which is still 1.6 times 10 to the negative 19. Charge C is positive 1 microcoulomb. And the distance is still 2 times 10 to the negative 6 squared. I think I can go second function enter and just change this to a 1. You get 3.6 times 10 to the negative 4? Zay, yeah? Direction. Repel or attract, Zay? Pardon me? Convince me. Yeah, unlike charges will attract. So direction? I would, since we use left, down. Yeah, so. How do I find the net force? Can I just add these up? No. Tip to tail. (7.2) times 10 to the negative 4. 3.6 times 10 to the negative 4. Okay, thankfully it's Pythagoras. That's going to be, and SOHCAHTOA. Oh, are we going to be using some trig buttons, Brett? Probably we need to be in degrees now since we're getting tricky with it. This squared plus 7.2 times 10 to the negative 4 squared equals square root. I think for a magnitude you'll get 8.05 times 10 to the negative 4 newtons at there's theta opposite adjacent mode. I am in degrees. And Connor, I took a blazing shortcut. I noticed that this divided by that is a half, so rather than type in all that scientific notation, I went shift tan of a half because that's what it... Anyways, and you get 26.6 degrees? 27 degrees? Yeah. 27 degrees. What of what? South of west. South of west. Yeah. Sorry? Down of left? I would probably take it, but I'd look at you a little weird. You could say below the horizontal or left and below the horizontal, but yeah. Since we've kind of done north, south, east, and west all year long, maybe that might work. No? Okay. What's your homework? Well, homework number 1 is study for the test. Homework number 2. Number 1? Yeah, sure. Number 5. Seven. 8. 10. That's overkill.